As well as providing interactive demonstrations, constructions and explorations, dynamic geometry software can stimulate discussion and encourage mathematical thinking. In this programme, we'll look at 2 lessons that show dynamic geometry in use. Andrea Willis and her Year 8 class.
The objective of today's lesson is to construct a hexagon using geometry sketchpad and then form a tessellating pattern. We need to create a short line, so just create a short line. Now what we're going to now do is rotate this round by the interior angle. We've actually got to decide what that angle is. Our exterior is 60, our interior, therefore this angle needs to be what? Darren?
120.
It's at 120 degrees, just press rotate and we've now got the line. Now we need to repeat this, obviously, until we actually create the hexagon. Once you've then done that, you can create a simple pattern inside and then follow the instructions to colour it in. Right? And then that's when we move on to try to investigate the tessellating pattern. Create a pattern inside and then colour that. It's such an instant picture, you can get them working. And we can get the objective met very quickly in the lesson and actually look at the tessellating pattern, as opposed to, like, if I was asking them to draw it, we'd probably not even get like one proper tessellating pattern at the end of it. Does that look right to you? Have they fit together?
Yeah.
Looks like they have to me. So what do you think you do to form the next one?
Rotate.
Rotate again, yeah. Excellent. Rotate. Have you done it?
Yeah.
Excellent. Right, now the question is, why have we got these all fitting together? What do all their angles add up to?
360.
360 degrees. So they're all in a complete turn, aren't they? That's adding up to 360 degrees, because each one of these was what degrees? What was it?
120.
Yeah, 120. So we had 120, 120, 120. All 3 of them fitted together.
360.
360. Therefore, it tessellated.
Yeah.
It's instant, and you're asking them to explain. You're asking them to give reasons why. Why does it tessellate? Why is that forming? How do we get the interior angle? So they've got to be able to know about interior, exterior angles to create the pattern and rotation as well, in order to be able to do all of that.
We built one of them and tessellated it, but you can only tessellate it twice.
So we need to make
another one
and then tessellate from there again.
Because they can actually spend more time on the reasoning and the proof, we can actually get a higher level of thinking, a higher level of learning, than rather than just getting them to construct and colour those patterns in. Why does this hexagon tessellate?
Because they, so there's one, and one of the sides fits with one of the other sides.
Yeah.
And then another triangle fits with the 2 triangles in the little triangle.
So all of these fit together, and how many degrees, to make them fit together, how many degrees are they actually forming then?
120 degrees each time.
120 there, 120 there, 120 there. Yeah, makes how many degrees?
360.
360, which is a complete turn. So therefore, they all fit together. I'd like to sort of think that they do actually appreciate the fact that they all do fit together, and because they fit together nicely, that the 120 degrees make 360, that's what I'm hoping that they actually get out of this.
Yeah, it was easier. I saw it's quicker and it's a better way to work out your angles and try and figure out how they fit instead of keep drawing it, because you can't really find out if you draw it, because you've drawn it and you can't really measure it.
Try that again. Now repeat with a pentagon. Now what we want to know with the pentagon is, do they all fit together to make 360 degrees?
See, them goes there.
Even with the software, pupils still have to be mathematically precise about what they're doing.
No, it won't, because it's already rotated by all the 120, isn't it?
Mine's gone wrong.
Oh, wow, it's just a big hexagon.
What have you done then?
We rotated it by 360 degrees. Because it would rotate by 120.
What did you actually rotate by 360 degrees?
All of it. All the 3 hexagons.
All of the 3 hexagons?
Yeah.
So,
had it like that. And
so what you've done is spun it. You spun it round.
yeah, there we go. So if we rotate it from there, we got to do 460.
Rotate. Do you want to rotate by 180 though?
No, 120.
120.
Yeah, it works again.
It's working again, but where's it fitting? Move it down a bit. There we are. So what you want to try to do is just experiment. So keep rotating and see if you can fill in the gaps then.
And how's the pentagon coming on?
Right, okay, so what you've got, these pentagons do not fit each other because when they rotate, they do not make 360 degrees. Excellent. So what do they make then? You've got 108, another 108, and another 108.
324.
Right, so what's that gap going to be then?
36.
36 degrees, excellent. So therefore, in order for a pattern to tessellate, what do we need to make sure actually happens?
It equals up to 360.
It equals up to 360, excellent. Well done. Brilliant work, Becky. Transform my teaching basically because the interest value of it, the motivational value of using Geometry Sketchpad and other packages like that is excellent. It's so visual, it's so instant, and you can actually demonstrate by moving things, and which you can't do if you've got a pen and a piece of paper.
Right, what we're going to look at first is just
Mike Hartnell and his Year 9s are going to look at the properties of some 2D shapes.
You're going to look at a 7-circle problem. And the idea of the 7-circle problem is it's 7 circles, each connected by the circumference and the radius. What your job is to do is to use the points of intersection to create shapes, and then tell me how you know it's that shape. Right, it goes back to the old thing of convince yourself, convince a friend, and then try and convince me.
Once they've created a shape, they have to justify their conjecture as to what it is.
It's more like a diamond, isn't it?
And the sides are parallel.
Is that a rhombus? Yeah, but the fact that these two are parallel, it's hard to work out.
Because that's a radius of those 3 circles.
So you think you found a rhombus there? How do we know that that's a rhombus?
No, rhombus because all the sides are radii of these equal circles, and the angles aren't right angles. Yeah. Well, we could also show that it's 2 equilateral triangles, which can be put together to make rhombus.
Excellent.
That also proves that they are all equal.
Okay, you've then got 2 triangles. All of those sides are the same length because of the properties of a circle. You can now tell me what this angle is in here, can't you?
That's 60 degrees.
And why is it 60 degrees?
Because all the angles inside an equilateral triangle are 60 degrees.
Okay.
Why is this a regular hexagon?
Right, so we know that all those lines must be the same size because they're all radii of circles.
Yeah.
Okay, and what about the angles then? How are we going to look at these angles?
If they're all the same length, all the lines are the same length, and they join up, then they have to be the same angles. I think. Yeah.
You think?
Yeah.
And you're convinced by it? Maybe you need to draw some more lines in to try and convince yourself. What lines could we draw in to help us with this?
You make loads of triangles.
Ah. And what would be special about those triangles?
They'd be equilateral, wouldn't they?
How do we know they're equilateral triangles?
Because that's the radius of that circle, that's the radius of that circle, and that's the radius of that circle.
Okay, so we're happy with the fact they're equilateral triangles, yeah?
Yeah.
So we've got 3 radii of circles.
Yeah.
So we know that they're equilateral triangles. What else do I know about an equilateral triangle then?
It's got all the same angles.
It's got all the same angles.
Of 60 degrees.
Right, so that's 60 degrees. So what can we say about that angle as well there?
That's 120.
Right, that must be 120 degrees. I think you pretty much convinced yourself it's a regular hexagon.
How do you prove that this is a rectangle?
Well, we know that it's a rectangle because these line A, side A and side B
Right.
are they're both the radius of a circle, so we know that they're both the same length.
Okay.
We know that they're parallel.
Using the software gives more time for pupils to reveal their mathematical thinking and for the teacher to address any misconceptions.
Because it's symmetrical.
Yeah.
Where's the line of symmetry? Where are you?
Well, the line of symmetry is through the middle.
Okay.
At that point,
that point, we know by cutting that will cross the middle, so we know that it must be in the middle.
Okay.
Drawing these lines, and we know that it's then they're going to be perpendicular to the side A and side B, and we know it's a triangle.
Right, perpendicular. Where are you pointing perpendicular there?
This line is perpendicular to side A, and it's also perpendicular to side B.
Right, did you create that as a perpendicular line?
Well, originally we hadn't, and then we checked it by creating a perpendicular line.
Okay. You've written down there that they're two equilateral triangles.
Yeah. And we know they're both the same size. They're both equilateral triangles, and they're both the same size.
Right.
So.
What can we say about these two triangles then?
They are equal.
How do we know they're equal?
Isosceles, because they share the same line of the equilateral triangle.
Right, so we do know that these two sides are the same.
Yes.
Yeah? What else can you tell me?
Well, that means that line will be the same, because they're the same length, so it must have the same length.
Right, we would need side, angle, side. Okay, so we need one other angle in there. What can you tell me about this angle and this angle?
They're the same. And
Why are they the same?
because
What do we know? When two lines cross, which we've got here,
the point of intersection, yeah.
right, what can you tell me about the two angles? Yeah. They're equal. Right, opposite angles where two lines cross must be equal. So these two angles must be equal.
And those triangles must be equal.
So if that side, that angle and that side are equal, that must be an isosceles triangle. That must also be an isosceles triangle. So those two sides are the same length. So you've got two perpendicular sides, you've got those two sides are the same length, and you've also got these two sides being the same length. Fantastic. And you've got yourself a rectangle. You can draw it on paper and almost write down your explanations, but you lose that talking about it. And I think that's actually quite important with the maths, and certainly when you're looking at explaining and justifying why these shapes are these shapes, that interaction by drawing it on the computer and by saying, well, how have you done that, actually does help them come to terms with what they're doing. Having floated around and seen most of you, I have to say I've seen some really, really good shapes. And actually, although at first you might have gone, oh, how on earth do I do that? By the end of it there, you've managed to prove that you have got that particular shape you said. So in some ways, you've convinced yourself, you've certainly convinced your friend, and in most of the cases there, you've managed to convince me as well. Anyone feel brave enough to come up and have a go on the board?
All right. I made a hexagon from I know all the sides are the same length because they're all radiuses of circles, but I wasn't sure whether the angles were the same. So to prove that they're all the same, I drew lines through the middle of the hexagon to make equilateral triangles. And I know that equilateral triangles, because they're all radiuses of circles, if you look, and so they're all the same length and they have all the same angles. So if they have 60-degree angles, then all the angles must be 120 degrees. So I made a hexagon.
Perfect stuff. Well done.